Hi everyone, today I'm continuing to look at question 14 of the 2020 Baulkham Hills Extension 1 trial exam. So I've already worked through question 14A and question 14B in separate sets of videos. Here we're looking at part C, which itself has two subparts, so I'll take a look at each of these in separate videos. So here we're going to focus on part 1. The setup to the whole question is we're told to suppose there are n different books and there are p identical copies of each of those n books. And we can assume that n and p are non-zero integers. So part 1 says if all the books are to be placed in a line on one shelf, in how many ways can this be done? So in other words, how can we arrange all of these books in a straight line as opposed to, say, in a circle or something else? So yeah, let's take a look. We're dealing with classic kind of combinatoric stuff here, so number of ways to arrange. I think you would have encountered this actually in the advanced part of the syllabus. So even though this is extension 1, I mean, you can be tested on all the advanced stuff as well. The questions just typically might be a little bit harder. So actually it was probably in the preliminary course that you learn all this stuff and you just got to carry it through over year 11 and 12. And there's really two rules that we're kind of applying here. Actually, even you could argue just one rule with its adaptation. So maybe in general, it's worth just noting the general rule here that if we have x different items, then the number of ways we can arrange x different items is equal to x factorial. And the idea there is that you've got x different items. If you're going to line them up, if you're going to arrange them, you've got x ways to pick your first item, and then you've got x minus 1 ways to pick the next item, and then x minus 2 ways to pick the next item, and so on. Each time you've got one less to choose from until eventually there's only one left. And so when you multiply all of those options together, you get x times x minus 1 times x minus 2 and so on, all the way down to 1. And that is what x factorial is defined as. So that's our most basic starting point. That's our general rule. We've got x different items. We can arrange them in x factorial ways. Now, there is a tweak that you have to make to that rule, which is if, for example, if y of those x items are identical, then the way you tweak it is the number of ways would be equal to x factorial on y factorial. So the way we adjust it, the way we make sure we're not overstating the number of ways is we divide by the factorial of the number of identical items. So the idea is, if some of these items are identical, then whether I pick, if I had, if they were red balls, for example, and they were all identical, whether I pick the first red ball or the second and put them somewhere, it makes no difference. So you can effectively count them as the same thing in terms of an arrangement. So this is how we adjust. Now, if, for example, let's say if y and z items are identical, so we've got x items in total, and out of those you've got y that are the same and then z that are a different type of thing but the same, then the number of ways you'd have there would be equal to x factorial on y factorial z factorial. And I'm just using these letters just because they're not letters that we've actually got in our question, just to make sure I'm not causing any confusion. So here's the generic rule that we're dealing with here. It's the number of ways to arrange stuff, noting that it's a very simple rule if everything's different. If things are identical, then we just need to make this adjustment where for every group of identical items, we divide by the factorial of that number. So keeping in mind those general rules, let's see what we're specifically dealing with here for 14C part 1. And maybe a little diagram might help. So we've got n different book types, so those book types are different, but for each of those different books, we've got p identical copies. So One way you might want to think about it is, let's just say we've got here, you know, I'll call this book 1. Maybe it's an actual title of a book, and then we've got, you know, another title, book 2, and then another one, book 3, and so on. And we're told that we've got n. We've got n different book titles, say, if you find that helpful. So across here, we're basically dealing with some integer n. But we're told for each of these books, we've got p copies. So, you know, we'll have another book 1, and then another book 1, and so on. And then the number of book 1s that we've got is p. And actually, it's the same with the number of book 2s. We've also got p and the number of book 3s, and all the way up to n. I won't draw them all up, but you get the idea. There's p identical copies of each of these books. So first of all, if we're thinking of the total number of items, what's the equivalent of x here? Our total books is equal to n times p. It's basically this square if we were to count up all the books. So it's n times p is the total number of books. The number of ways to arrange those books would be equal to n times p factorial. And I've written that in brackets quite deliberately to make sure you don't think it's n times p factorial. It's n times p, whatever that is, the factorial of that number. And that's effectively just the equivalent of this here. But we know we've got identical copies. In this case, it's not y and z being identical, it's p every time. Every time we've got p identical copies of b1, p identical copies of b2, and so on. So we need to adjust this. So actually, the number of ways is not just np factorial, it's actually we've got to divide, and what we have to divide by is, well, first of all, p factorial to deal with the identical b1s, and then by p factorial again to deal with all the p2s, because it's p copies of those, and so on. And we got to keep dividing by p factorial n times. Basically, we've done this n times because there's n identical there's n sets of identical copies of books. So really, in terms of how we can just kind of clean this up a little, it's np factorial divided by p factorial to the power of n, because we're multiplying it together n times. And you know, if the number of identical copies was different, we'd just be dividing by the factorial of each different number. But because it is p every time, it's p identical copies of each, it becomes a bit simpler. It's just p factorial to the power of n. Panic boom! And that's it. That's how you can answer that question. So really we're just making use of, I guess you could argue, that the most basic concepts in terms of counting and a number of ways of arranging items. We start with our most basic rule, which is if they're all different, it's just x factorial. But if some of them are identical, we divide by the factorial of how many are identical. So in our case, it's just dividing by the same thing every time, and I think that's the key. Maybe some students out there in Extension 2 might forget to do that denominator and just do np factorial, or you'd hope not, but I guess that's a possible error. But yeah, as long as you remember to make that adjustment, I think there's not a lot of working required for this question. I think it's just, yeah, getting a grip with what you're really dealing with, and drawing a simple diagram like this is often a helpful thing to do. It can often help give a bit of clarity as to, you know, what are you really dealing with here. So yeah, hopefully you found that explanation helpful and you could follow along with all that. In the next video, I'll take a look at part 2 of this question. All right, tick boom.